Welcome to Lesson 24, Exponential Functions. Probably in your mathematics career so far, you haven't seen a whole lot about exponential functions. But they're very important, and we haven't discussed them until this time because we finally have enough knowledge to investigate these very important functions. Why are they important? Well, there are many things in the real world that grow exponentially. What does exponentially mean? Well, in an exponential function, we have a situation where the x, or the variable, is in the power or exponent. Let me give you an example over here. Let's go to the board. And of course, I need a piece of chalk. It's always a good idea to have chalk when you go to the board. We have a function like y equals ab to the x power. B, you'll recall, is called the base. A is simply a coefficient. X is the exponent or power. And as we'll see, exponential functions cause values of y to grow quite rapidly. Now, can you think of something in this world that's been growing quite rapidly, in fact, is growing faster and faster all the time? One thing would be to look at the population of the world. Ever seen charts on the population of the world? Every time we add 1 billion people, it takes fewer years. The population of the world is doubling much more quickly now than it was, let's say, 50 or 100 years ago. The growth of population is exponential. The national debt of this country has been, for the past, 20 or 30 years, exponential. I'm no expert on economics, but obviously you read in the paper and you recall from previous presidential campaigns concerns about the growth of the national debt. It's growing exponentially. We'll also see later on there are things that fall off, that reduce exponentially. For example, one example I want to give now is what's called a learning curve. Let's say, for example, right now I gave you a list of 50 gibberish words. That is, words that had no meaning. You learned the word, you memorized the word, and probably if I gave you enough time, you could have memorized all 50 words. Let's say later on today I gave you a test to write as many of those words as you could remember. You probably would remember most of them. And then tomorrow I gave you another test, and next week another test, and next month, and in 6 months, and in a year, and 5 years from now. And pretty soon you'll see that you'll lose most of those words. In fact, by another week from now, you'd probably have forgotten most of those words if you haven't had a chance to look at them. And after a while, what would happen is you'd probably be down to 1 or 2 words that for some strange reason you continue to remember. That fall off of your knowledge of those words would be an exponential function, as we'll see later on. But before we go in and look at exponential functions and how to sketch them, and exponential equations and how to solve them, what I want to do is review some ideas about exponents that hopefully you learned way back in 7th or 8th grade, that you've used in Algebra 1 and you're familiar with, but just to be sure, because sometimes things kind of slip to the back of the old brain, I want to remind you of those. Let me take a sheet of paper here so I don't forget any, and talk about properties of exponential numbers. Let me go ahead and erase this. This is, again, the base form of the exponential function. How about this? We take the base b, we raise it to the m power, and we multiply it by b to the n power. Hopefully you recall that rule says that when the bases are the same, you keep the base and add the powers. Quite frankly, I am not going to take the time at this point to show you why these work. If you don't know why these work, you should find out, because there's a reason for each of these rules. But again, we don't have the time here. This really goes back to pre-algebra skills. If you divide two numbers with the same base, you keep the base and subtract the powers. And by the way, these rules will come into play in our next lesson. We talk about logarithms, which are the inverse functions of exponential functions. So it's a good idea to write these down just to make sure you have them under control. We also know if we take the base and raise it to a power, and then raise that to a second power, another power, that we multiply the powers. That's b to the mn power. We multiply the two powers. We also know that any base to the 0 power is 1. Now, I realize for many students this makes no sense, because you'd say, well, anything to the 0 power should mean I have none of these b's, and therefore I should be 0. But it is 1, and again, if you don't recall why, you might even ask your teacher or look back at an old pre-algebra book to find out why. It's my belief that the students, again, should know why, but you should know this. This is important. And the last of these rules is that if you have a negative power, b to the negative m, that is the reciprocal. The negative power is the reciprocal, and that's 1 over b to the m power. And for example, some numerical examples here that we could see, let's say 3 to the second times 3 to the third would be 3 to the fifth. 4 to the sixth divided by 4 to the fourth would be 4 to the second power. If I had 5 to the second to the third power, that would be 5 to the sixth, since 6 is 2 times 3. Anything for, well, 17.38 to the 0 power is 1. As I like to say, your social security number or telephone number to the 0 power is 1, because anything to the 0 power is 1. And for example, 8 to the negative 2 power is 1 over 8 squared. Okay, so that's a quick review of some ideas about using exponential notation. Quite important, because we're going to be able to use those as we solve exponential equations and as we sketch the graphs of exponential functions. Let's take a look at a very simple exponential function, and we'll do that at the easel. Let's take a look at y equals 2 to the x power. Again, it's an exponential function. You have a base of 2, and the x is in the exponent. Okay? And we're going to sketch this just as we did other type things by plotting points. I mean, if we don't have any idea necessarily what this looks like, it's probably a good idea to plot points, get a feeling for what the graph looks like, and then use that knowledge to graph other exponential functions. So let's go ahead and put axes in here. And let's go over here and set up a little table. X, y. Let's start out. Let's put some negative numbers in. How about negative 2? Negative 1, 0, 1, 2, and possibly 3. Okay. Let's see. And what I'm going to do here is I'm going to allow each of these boxes to represent 2, so that the 2, 4, 6, 8, etc. And I'm going to do the graph in another color in black so we can see it very clearly. Now, what happens when x is 2? What is 2 to the negative 2? Remember, the negative power means the reciprocal, so 2 to the negative 2 would be 1 over 2 to the second, or 1/4. Put that in here. And plot the point. When x is negative 2, y is 1/4, right here. Notice we cannot raise 2 to a power and get a negative number. It's impossible. So we're never going to get a negative number. We put in negative 1 for x, we get 2 to the negative 1, which is 1 over 2, which is a half. We put in 0, we know that 2 to the 0 is 1. 2 to the 1 is 2. 2 to the second, or 2 squared, is 4, and 2 to the third is 8. So let's plot those points. Negative 1/2 would be someplace over here. Make a little bigger dot. 0, 1 over here. 1, 2. 2, 4. And 3, 8. Now notice what happens. As the points move to the right, they go up faster and faster, and that's exactly what happens with an exponential function. It goes up faster and faster, rising exponentially. What happens back here? Well, can we raise 2 to a power and get 0? No. Let's put in a very, very negative number, 2 to the negative 1,000th power. That's 1 over 2 to the 1,000th, a very, 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 very small positive number, which means this graph will get closer and closer and closer, but never touch the x-axis. And therefore, the x-axis is its asymptote. Again, close but not touching. So it looks like a typical exponential function starts off very slowly, rising very slowly, and then all of a sudden grows rapidly. A good example of that is, for example, a new product. Someone brings out a new product. Very few people hear about it at first, so the sales are rather small. Then those people start telling their friends, the company starts advertising, people hear good things about the product, and what happens? Sales grow. And the more they grow, the more people find out about it, word of mouth spreads, the company is making money, so they have more advertising, and they're selling more product, and the growth is phenomenal. Unfortunately, for most stockholders and business owners, this doesn't happen forever. But at least in the initial part of the product development, this is what you hope. If the product is to be successful, it's going to grow, its sales are going to grow exponentially. So this here is y equals 2 to the x. We're going to look at some other graphs right now. Let's look at the next visual, which should show us y equals 2 to the negative x. Okay, now remember, y equals 2 to the negative x. We can know that should be y equals 1/2 to the x, but to prove it to you, on this visual, I have an intermediary step that says if 2 to the negative x can be written differently, it can be written as 2 to the negative 1 to the x. Remember, when we raise a base to a power, we multiply powers. And therefore, 2 to the negative 1 to the x is 2 to the negative x. And 2 to the negative 1 is 1/2. So another way of writing 2 to the negative x is 1/2 to the x. And let's see how we graph that. The next visual shows us a roster of points for 1/2 to the x, which of course also can be written as 2 to the negative x. Notice now when we plug in x is negative 2, 1/2 to the negative 2, well, that says take the reciprocal of 1/2, which is 2, and raise it to the positive 2. So the answer is 4. So as x gets more and more positive, notice the values of y become smaller, but they never become negative because we cannot raise a positive number to a power and get a negative number. In fact, we can't get 0. Let's look at the next visual, which has the sketch of those points connected with a curve, y equals 1/2 to the x, or it could be written y equals 2 to the negative x. Okay? Notice the curve starts off and drops rapidly as you go from left to right in x values. And then it sort of levels off and gets closer and closer and closer to the x-axis, but it never touches. So once again, the x-axis is an asymptote for this curve. And this kind of curve can be used also in terms of, for example, that learning curve I talked about earlier. Remember we said that if you memorize those 50 gibberish words, fairly quickly you'd forget most of them. So in the first few days or weeks, most of those would disappear from your memory. And therefore the curve would fall rapidly. And then you'd reach a point in time where you might lose a word or a word here or a word there, but basically the loss of knowledge will be very slow to decrease. Okay? And therefore, that's what's called a negative exponential. Because remember, the original way we wrote the function was y equals 2 to the negative x. Well, so far we've looked at simply the base 2 to a power. We chose 2, quite frankly, because if you use a bigger base of 3 or 4 or 5, you need a huge piece of graph paper because, for example, 4 squared is 16 and 4 to the third is 64, and we don't have that many boxes on our graph paper here. Now, we want to look at next a little step up, a situation where we actually have a coefficient in front of our base to the x. And the next visual shows us that. We have 3 times 1/2 to the x. And quite frankly, all we've done to get this roster of points, we've used the same values of x that we used in the previous function. We've simply multiplied the answers by 3. That is, for example, to find 3 times 1/2 to the negative 2 power. Remember you learned some time ago that you do powers or exponents before you multiply or divide. So 1/2 to the negative 2 is 4, and times 3 is 12. Thus, the point -2, 12. Okay? In our next visual, we see the sketch of this graph with the points plotted, and you'll notice it looks just like y equals 1/2 to the x, except we're expanding. The numbers are bigger because instead of starting at -2, 4, it starts at -2, 12. We've multiplied everything by 3. What do you think would happen if we had done 1/3 times 1/2 to the x? Hopefully what you said is we kind of scrunch things up, because instead of multiplying by 3, we'd multiply by a fraction 1/3. Now, let's take a look at this graph that we're looking at on the visual, because this is an example of something that you will come across, if you haven't already, in your science classes, something called half-life. Because what happens in half-life is every half-life period, the amount of radioactive material left is halved. Let's talk about that, for example. In fact, let's go to the board and see if we can demonstrate that. Let's erase all these rules. Hopefully you now have them. And basically what we have with half-life is this: the x-axis is year or time, and this is the weight of the radioactive material. And let's say the half-life of something was 100 years. So each of these tick marks would be 100 years. 100, 200, 300 years. And let's say at some time, present day, for example, being now 0, we had 1,000 pounds of radioactive material. What would happen? At the end of one half-life, we would have half as much. That 1,000 will be multiplied by 1/2 to the x, where the x would be the number of half-lives, in this case one half-life, and 1,000 times x would be 500. So here's our 1,000, here's 500 at the end of 100 years. 100 more years would go by, and now we would have 1,000 times 1/2 to the second, which is 1,000 times a fourth, which would be 250. Halved again. And at the end of 3 half-lives, 300 years, we would have 1,000 times 1/2 to the third, which would be 1/8, or 125 pounds. And we'd have this curve, and notice, theoretically, we'd never ever have 0 pounds. But actually what would happen is over many thousands of years, the material would be reduced to just molecules of this radioactive material. Excuse me. This is quite important, this notion of half-life, because, for example, because of radioactive waste from nuclear power plants, and I assume also from nuclear weapons that were needed for the Cold War, we have a stockpile of radioactive waste material. If this material, for example, has a half-life of 100 years, 300 years from now, there'd still be 125 pounds of that radioactive stuff left for every 1,000 pounds we have today. And quite frankly, some of the radioactive waste we have, I believe, has a half-life much greater than 1,000 years. Much greater than 100 years, in fact, as much as 1,000 years. So that's something to seriously consider when we consider our Earth and the ecology therein in terms of waste matter that's radioactive. And again, all this is based on the notion of the exponential function, just like the one we looked at. Okay. Now, we want to look at one more, because one thing we haven't done is we haven't looked at what happens if the coefficient, that a in ab to the x power, is a negative number. Let's look at the next visual, which shows us y equals -2 to the x. Notice that negative is in front of the 2 and is not in parentheses. So again, we're multiplying by a negative after we raise x to a power. And look at the graph. The graph in white was the original graph we did, y equals 2 to the x. The graph in blue is the graph of y equals -2 to the x. Notice what we've done. In fact, anytime we multiply a function by a negative, all we do is reflect it, or if you like, flip it around the x-axis. So certainly y equals negative 2 to the x would be a great function to use if we had something that was decreasing, and initially decreasing very slowly, and all of a sudden was decreasing very rapidly. This possibly could be something, for example, like what happens to a stock when people start to sell it. The price goes down, and people hear this, the price is going down, so they sell it. And the price goes down more because there are fewer people buying and more people selling. And as the price goes down more, people panic, and pretty soon everybody wants to sell their stock, and since people are interested in buying it, they've got to lower their price drastically, and the people who sell it at the very end of this period wind up losing a great deal of money because what you have is an exponential situation, very similar to perhaps to this y equals negative 2 to the x. Okay, I think we've had a pretty good look at exponential functions in terms of graphs. You'll see more of this in later courses for sure. But let's take a look at solving some of these exponential equations. Let's go to the board and take a look at a typical exponential equation. So we'll erase our half-life graph. And let's take a look at an equation like this. There is an exponential equation. Equation and the exponent contains a variable. Very important. That's what an exponential equation should look like. Well, basically, the way I like to solve exponential equations at this point in time is to get both terms on both sides of the equals to have the same base. That is, we need to make 81 a power of 3. Is 81 a power of 3? Well, let's see. 3 squared is 9, 3 cubed is 27, 3 to the 4th power is 81. How nice. Well, of course, if this had been 3 to the x equals 72, you couldn't have done it right now. The next lesson will give us some hints at how to do that, but we're not up to the next lesson yet. We're still talking about solving these exponentially. So, 3 to the 4th. Now, let me ask you a very, very simple question. Two numbers are equal. They have the same base. What do you know about the power? What you should say is that the powers have to be the same, because you couldn't have 3 to the 4th and 3 to, let's say, the 5th be the same number. That's silly. It couldn't be. So if 3 to the x and 3 to the 4th are equal, and 3, of course, is equal to 3, then x must equal 4. And guess what? We're back to a very simple linear equation. In fact, the simplest linear equation. If x equals 4, what does x equal? X equals 4. And we can check that. 3 to the 4th indeed is 81. So we solve the exponential equations by getting both sides of equals to have something that has the same base. And then we set the power as equal. And we wind up generally with a linear or possibly a quadratic equation, something we know how to solve. So let's look at the next visual. The next visual shows us the equation 8 to the 2x equals 16 to the x plus 1. This is a bit different because we don't have the same base. So you could say, well, I guess we can't do this. Well, let's stop for a second. I wouldn't be giving you this problem if we couldn't do it. The question is not that we have to be able to make 16 as a power of 8, but we've got to get both terms having the same base. That is 8 a power of a number that 16 is also a power of that number too? And as you can see in the second line, which is highlighted, 8 and 16 are both powers of 2. So we have 2 to the 3rd in parentheses, that's 8, raised to the 2x power. And on the other side of equals, we have 2 to the 4th in parentheses, that's 16, raised to the x plus 1 power. Now we use the rule we talked about earlier. When you raise a base to a power, you multiply the powers. So on the third line, which is highlighted, we see 2 to the 6x equals 2 to the 4x plus 4. We've multiplied x and plus 1 by 4 to get 4x plus 4. Now we have an equation equals The bases are the same, and therefore we set the powers equal to each other, which is exactly what we'll do in the next visual. We have 6x equals 4x plus 4, and we're back to a simple linear equation. We subtract 4x from both sides, we get x equals 2. We're not done, we need to check. We go back to the original equation, 8 to the 2x. Well, if x is 2, 2x is 4. So 8 to the 4 must equal 16 to the to the x plus 1. X is 2, 2 plus 1, indeed, yes, that's right, x, it's 3. So is 8 to the 4th equal to 16 to the 3rd? Most of you probably don't walk around knowing your powers of 8 and powers of 16. A good use of a simple calculator. 8 to the 4th is 4,096. 16 to the 3rd is also 4,096. Our equation checks. The answer is x equals 2. Okay, let's take a look at the next visual. Now, what is different about this equation? You'll notice that on one side we have a 9 to a power. On the other side we have a fraction, 1/27th, raised to a power. That's a bit different, but this is still an exponential equation because it's equals and the variable is found in the exponent. What do? Well, as shown, we need to get both bases the same. Well, we look and see, I say 9, I know is a power of 9. It's also a power of 3. The fact that it's a fraction, 1/27th, we don't worry about. We know that it's a reciprocal, and reciprocals are simply negative powers. So the question is 27 a power of 9? And the answer is, it is not. It is not a power of 9. Is it a power of 3? Yes, 27 is a power of 3. In fact, it's 3 to the 3rd. Well, if 27 is 3 to the 3rd, we should know that 1 over 27 is 3 to the negative 3rd power, the reciprocal of 27. And thus, we've changed the 9 in parentheses to 3 to the 2nd. We've changed the 1/27th in parentheses to 3 to the negative 3rd. And now we use exactly what we did in the previous problem. We multiply, because raising a base to a power, you multiply the powers, and we get 3 to the 2x plus 2 equals 3 to the negative 3x plus 9. Now we're back in the situation. We have an equation, equal bases. We set the powers equal to each other, and that's what we've done in the next visual. We have 2x plus 2 equals negative 3x plus 9. We're back to where we were many, many lessons ago, solving a simple linear equation. We want to get the x on one side, so we add 3x to both sides. We subtract 2 from both sides to get the number term on the other side. We have 5x equals 7, and we get x equals 7/5. This leads to an interesting check because 7/5 is a fraction. And by the way, we go back into our original problem, 9 to the x plus 1. Well, x plus 1, if x is 7/5, that would be what? That would be 12/5. And 9 to the 12/5 means take the 5th root of 9 and raise it to the 12th power. I don't think you can do that in your head, and probably using your fingers won't help. Again, we call for the calculator. I took a calculator and raised 9 to the 12/5 power, and I got a number that was 195.0661995 ... because it's not a precise number. This is close enough. Okay? Then I did the same thing. We said, let's see, negative 3, we have 1/27th to the x minus 3. We replace x with 7/5, and 7/5 minus 3. So I raised 1/27th to that power and got 195.0661995 ... So the two answers, the left side and the right side of this equation, when we plug in x equals 7/5, are precisely the same. And therefore, it checks. And the interesting thing about the check is we got this crazy number with all these decimal places in it because we were dealing with, in effect, irrational terms because of the 5th root business. But the fact is, using a calculator has helped us to check to see that for our original equation, the only answer that works is x equals 7/5. All right, what have we done? We've looked at the meaning of exponential functions and the use of exponential functions. We've seen how to graph exponential functions by plotting points and looking at the typical kind of exponential function. We have also looked at exponential equations and how to solve them by simply getting both terms on the left and the right to the same base, set the powers equal, and solve the equation that results. In the next lesson, Lesson 25, we will take what we've learned here and expand it by using logarithms and investigating logarithm functions. What's a logarithm? You'll find out in the next lesson.